Direction of induced current. Induced current in a loop. Okay. So if you have a current carrying wire through which a current I increasing, an increasing current I is flowing through this wire, and a circular loop, one placed above and one placed below the wire. The question is, how will you find the direction of induced current in the loop? So obviously this wire has some magnetic field, magnetic field of the wire at the center of the loop is towards the observer. See, towards the observer. So magnetic field is towards the observer. And since current is increasing, so magnetic field of this increasing current will also keep on increasing. Obviously the flux phi, which is B into A, so with increase in I, B will increase, and if B increases, phi will increase. Flux linked with the coil will increase. According to Lenz rule, the induced current will flow in the circuit in such a way that it will oppose the reason, the cause which produces it. So reason is increasing magnetic flux will induce the current. So then the loop will set up the current in such a way that magnetic field which was increasing due to increasing I should be opposed. So how can you oppose the magnetic field? By applying the loop its own magnetic field opposite to the field of this current carrying a straight wire. So current carrying a straight wire has magnetic field here towards the observer, okay, dot. So the loop must have the field into the plane of whiteboard, into the plane. So the current in the loop should be clockwise. So the current will be in clockwise direction. And if you place the loop, circular loop just below the wire, then the scenario will be just reverse. So in upper part it is clockwise. So here it is anti-clockwise. So anti-clockwise is this direction. So remember, if this is a for your memory aid, you can just remember it. If I is increasing, then induced current will be such that it will oppose this I, increasing I. Since I is increasing, so if current here it is in opposite direction to this current, then it will oppose this current. Here also you will see the current in the wire is from left to right. So current in a circular loop is such that this direction will oppose this current. Actually it is not, current will not oppose the current, but just to keep it in your mind, just to do it quickly. So if it is I increasing, on the other hand, if you have a wire through which current is decreasing, I decreasing. Now can you tell me in which direction the current will flow in the loop? Yeah? Who can tell me the direction of current? In the upper loop? Yeah, tell me. In the upper loop, since I is decreasing, so it will support, the current will be such that it will support this decreasing current anti-clockwise in upper loop. So it is very much clear that if I is decreasing, means magnetic field, first you have to reveal the magnetic field of this current carrying wire. Magnetic field of this current carrying wire at the center of the loop is towards the observer, towards yourself. Okay. If you are facing the whiteboard, then magnetic field will be towards the observer, perpendicular to the plane of whiteboard and towards the observer. In other words, you can say outwards. In other words, you can say upwards. Okay. So since I is decreasing, so magnetic field is decreasing, because magnetic field of a straight wire B is what? Mu naught by 4 pi 2I by this distance, whatever is this distance, suppose it is R by R. So since I is decreasing, so B will decrease. Decrease in B will result a decrease in flux. So flux is decreasing. Now the current in the loop will be such that it will try to reduce this flux. So how to reduce the flux? And not by reducing the area of the loop, by opposing this magnetic field. Since magnetic field of the wire is towards the observer, so loop should apply field in what direction? Opposite to, no, current is decreasing, so flux is decreasing. So the current will be such that it will support the decrease of flux. Means it will resist the decrease. So the current in the loop should be such that its magnetic field will be in the same direction as that of the current carrying wire. So current carrying wire has magnetic field along this direction. So if the loop is also applying magnetic field in the same direction, magnetic field being the vector quantity, two fields in same direction, now the resultant will be plus. I mean V1 plus V2. Now, so due to decrease in I, the field of the wire was decreasing. Now, due to the magnetic field of the loop in the same direction, now the magnetic field is stopped by decreasing. So that's why magnetic field of the loop is along this direction. So current should be in anti-clockwise direction. And just opposite to this case. So it should be in clockwise direction. It should be in clockwise. Remember, since I is decreasing, so current in the loop will be such that this current and this current will be in the same direction. If two currents are in the same direction, then they will be added. Actually, it is not adding. So if I is decreasing, then this current will stop from its decreasing nature. And similar way, since I is decreasing, so current in the loop is again in the same direction, again in the same direction. So easy to remember, easy to answer it. Now I can ask you the other question. I is decreasing. Now tell me, I is decreasing. In which direction the current will induced in the loop? Upper loop, lower loop? Yeah. Since I is decreasing, so in upper loop, the clockwise, I decreasing, so current will be in the same direction. And here also in the same direction. So now in the first loop, upper loop it is clockwise, in the lower loop it is anti-clockwise. Anti-clockwise, ACW. And here it is clockwise. This way you can do. Yeah? Same explanation is there. If current I is decreasing, magnetic field of this wire at the center is, yeah, into, that is away from the observer, into the plane of whiteboard, into the plane of whiteboard. And since current is decreasing, so magnetic field is decreasing. Now loop will resist that decrease. So loop will also apply the field in the same direction. Field being the vector quantity, and two fields in same direction gets added. So magnetic field of the loop should also be in the same direction, that is into the plane of whiteboard, pointing inwards. So what should be the current in the loop? So this is the finger, direction of finger, rotate the finger, clockwise, clockwise, clockwise. Then only the field of the loop is in the same direction as that of the current carrying wire, straight wire. And if you see the magnetic field of this current carrying wire at the center, then this is lying below the wire. So magnetic field is towards the observer. Now this is towards yourself. Okay, now I am writing dot here and here it is cross. These are the magnetic fields of current carrying wire at the center. Now again I is decreasing, magnetic field is decreasing. So the loop will induce current in such a way that it will stop its decreasing nature, that is decreasing flux. So how can it stop it? The magnetic field of the loop should also be in the same direction, that is along outward direction. So that's why the current should be anti-clockwise. Current should be anti-clockwise. But it will be easier for you to remember if the current I is decreasing, then current in the loop, induced current will be such that this I, this current and this current should be in the same direction. This current and this current should be in the same direction. But if I is increasing, see, if I is increasing, then this current and induced current should be in opposite direction. Should be in opposite direction. So in case of increasing, opposite direction. In case of decreasing, same direction. This way you can locate the direction. Now I can ask, suppose I is increasing. Okay. Now tell me in which direction the induced current will be developed in the two loops. Yeah? I is increasing, so it should be along this direction. Because current in the wire is from right to left and is increasing. So current in the loop will be such that it will oppose this current. And what about this? Yeah. So this is clockwise, this is anti-clockwise. So these four examples are enough to make it comprehensive. I think you don't have any doubt. Clear? Everything is clear? Okay, okay. Moving towards that motional EMF. Yesterday we have finished motional. Oh, I have not taken the snapshot. Okay, okay, I can make the figure once again. Okay. Uh, okay, okay, okay. I increasing, so it should be like this. And here it is. Take the snapshot. The first one is question number 1. Okay. Now, in the previous lecture, we have finished the motional EMF part. If you rotate a rod in the magnetic field, then induced EMF developed across its two ends. So that we have shown half b omega L square if it is rotated at some angular velocity omega, constant angular velocity omega. Do you want to recapitulate the same thing again? Yeah? Or it will be okay? That is induced EMF in a rod moving, rotating in magnetic field. That part is clear? Now I am doing one question based on that concept. If you have magnetic field like this, okay, and a rod of L say, I am putting one rod, thin rod, okay, and the rod is moving at some angle theta. This theta, actually this is also theta with constant speed v inside the magnetic field. Magnetic field, the rod is in the shape of letter L. L looks like L, and this part has length, suppose small l, this is also small l. The rod is moving with velocity v. Now you have to find the potential difference between the point P and Q, or EMF between the point P and Q. How will you find the potential difference? Remember that induced EMF E equal to BLV if all the three BLV perpendicular to each other. All the three parts BLV. But if there lies some angle between the L and V, they are not mutually perpendicular to each other, rather they are some angle theta, then the expression E is equal to BLV sin theta also, sin theta term. Actually, if you take the component of L along this direction, that is effective length, you just consider, then if this angle is theta, this component will be called L cos theta and this component will be L sin theta. Now this component, this is L, so along this direction, this is L cos theta, along this direction, it is L sin theta. So then what is the effective length of the rod? if you have a L-shaped rod, then take the effective length which will be perpendicular to, V as well as B. Now all the three parameters, that is magnetic field B, length L and V, all should be perpendicular to each other. Then induced EMF is BLV. BLV, magnetic field, length and V, speed, velocity. So then induced EMF E is equal to, that is induced EMF between the points P and Q. P and Q is equal to, see, for this part it is B L V sin theta, and for lower part this is also B L V sin theta. So the effective length is 2L sin theta, B L V sin theta. Now just add these two. This is 2BLV sin theta is the induced EMF between the points P and Q. 2BLV sin theta. Okay. Now moving towards some another question. An aeroplane moving with some velocity. The wings, this is the wings of aeroplane. Anyhow, I can make it like this. So the wing span is 25 meter long. That is the distance between the ends of the wings. Both sides, it is, the whole length is, L is given to you. L is, say, 25 meter. Okay. It is moving with a velocity of 5 by 18. So multiply, suppose 360 kilometer per hour. So in meter per second, it's how much? In meter per second, 360 into 5 by 18. So 18 to the, so it's 100 meter per second is the velocity of the aeroplane. Magnetic field, the horizontal component of Earth's magnetic field, BH. So BH may not be given to you. Magnetic field at some place from where the aeroplane is flying. Now magnetic field B is given to you. This B is, suppose, 0.4 Tesla. 0.4 Tesla. So that is 0.4 Tesla. Or sometimes it may be given in Gauss. And you know, 1 Gauss is 10 raised to minus 4 Tesla. If it is given in Gauss, you can convert it into Tesla. I am writing the formula. 1 Gauss is equal to 10 raised to minus 4 Tesla. Okay. So 0.4 Tesla is the magnetic field. Deep at that place, angle of dip. Angle of dip is also given to you. And deep at that place is, suppose, 30 degree. 30 degree. Now how will you find the induced current, induced EMF across the wings of the aeroplane? I mean, between these two ends, what is the induced EMF? Find the induced EMF between the end point of the wings. Say I am writing point here P, here Q. Okay, just take the snapshot. I will rub the upper part. Yeah, taken. Okay, so I'm rubbing this upper part. Now the problem is vertical component of magnetic field. Now you need to know this V and L are mutually perpendicular. Suppose the aeroplane is moving along this direction, V, L is perpendicular to this, wing is perpendicular to this, And then the moment you get the magnetic field perpendicular to the wings, that I mean perpendicular means vertical component of Earth's magnetic field. So then how will you find the vertical component of Earth's magnetic field? Vertical component BV is how much? That is B sine delta. Okay, B is given to you. Sine delta is sine 30 degree. So 0.4 into sine 30 degree is how much? Half. So it's 0.2 Tesla is the vertical component of magnetic field. And then induced EMF between the points P and Q. That is the end point of the wings. So then it is equal to BV L sine V, BV L V, BV L V. That is vertical component of magnetic field. L, the span of the wing, and V, velocity, speed. So then BV you have calculated 0.2, L is 25 meter, and V also you have calculated. It is 100. Multiply all this. So you will get how much? It's 0.2. So 55, 500 volt. Am I right? 500 volt. So total 500 volt potential difference exists between the point P and Q. If it is moving with a velocity 360 km per hour, 360 into 5 by 18, convert this into meter per second, and then magnetic field at that place is 0. Earth's magnetic field. Earth's magnetic field is 0.4 Tesla, and delta dip angle at that place is 30 degree. So then what is the induced EMF across the ends of the wing? This way you can calculate it. Okay. Now the another type of question, you just take the snapshot. I will rub it. Taken? Yeah. Because the formula BLV is valid only when all the three, magnetic field, length, and V, should be perpendicular to each other. Otherwise, you will take BLV sine theta, and see B sine theta is nothing but BV, vertical component. Okay? And magnetic field is given to you at some place. Magnetic field is given. So then magnetic field has two components, one horizontal and other vertical. One horizontal and other vertical component. Okay? This is Earth's resultant magnetic field. Earth's resultant magnetic field. Horizontal component is B cos delta. Vertical component is B sin delta. That we have discussed a lot in the chapter magnetism. Earth's magnetism. Remember that dip, declination, horizontal component of Earth's magnetic field. Clear? Now you have one ring. You might have seen the ring of cycle. Metallic ring. It looks like this. And here is the axle. And so many spokes are connected. Have you seen spokes? So how many spokes are there? Suppose 10 spokes. Total 10 spokes are there. So total number of spokes is equal to 10. Consider it as 10. Okay. Now this is rotated in a magnetic field. And magnetic field is perpendicular to the plane of the ring. Everywhere cross. Uniform magnetic field exists with B equals to, suppose, 0.4, or I am taking vertical component. This magnetic field is acting vertically downward, and this B is equal to, and anything we can take. So 0.2 or 0. 6 Tesla. Okay, this is the value of magnetic field. And this magnetic field exists in this region, uniform magnetic field acting perpendicular to the plane of the ring, pointing inwards, cross, cross, cross. You know the meaning of cross and the meaning of dot. Now B is 0.6 Tesla. If it is rotating with a velocity, angular velocity of, suppose omega is given to you. Suppose this is 120 revolution per minute. What does it mean? The ring is rotating about its axis with an angular speed of 120 revolution per minute. Means in 1 minute it is completing 120 revolution. So how will you convert into radian per second? So then omega is 120, and in one revolution the total angle subtended at the center will be 2 pi radian by 60. 1 minute means 60 seconds. Should I cancel? So it's how much? 4 pi radian per second is omega. Now if length of the spokes, it is 10 centimeter, each spoke has length 10 centimeter, which is 0.01 meter. 10 by 100, now 0.1 only now. So it's 0.1 meter. Now find the induced EMF across the ends of his spokes connected between the ring and the axle. Say I am writing this point P, here is P, here is Q. So find the induced EMF, find the induced EMF across the ends of a spoke. Yeah? So how will you find it? Yeah, L is 10 centimeter given to you. In the previous class we have derived one formula, induced EMF, if you rotate a rod with angular velocity omega about its one hand. Remember, it's magnetic field cross everywhere, and you are rotating this rod, spokes, whatever, about this axis with some angular velocity omega, constant angular velocity omega, and L is the length. Then what was the expression for induced EMF? E is equal to, remember, half, yeah, 1 by 2 B omega L square. Am I right? Half B omega L square. You can verify it from your notes. In the last lecture we have discussed induced EMF between these 2 points is equal to half B omega L square. So using this formula only, this E is equal to half B omega L square. Okay, half B is given to you, 0.6, 0.4, 0.2, 0.1, anything it may be, into omega is given to you. Omega is how much? This is 4 pi radian per second. Convert this into radian per second, SI unit. Into L. L is how much? 0.1. Square it, L square. This much will be the answer. So if you multiply 0.3, this is 1.2 pi into this is 0.01. Am I right? So it's how much? 0.012, am I right? Pi volts. If you put the value of pi also, which is 3.14, multiply these two, you will get the final answer. But I don't want to waste the time in multiplying the things. Okay, you can find it. So this much is the induced EMF across the ends of the spokes. Now if I ask you, total number of spokes is 10. Okay, number of spokes are 10. So what is the total induced EMF between a point on the axis and a point on the ring? So then what will be your answer? What will be the total EMF? Yeah? Anybody else? Anybody else can answer? So then each spoke has same induced EMF. Induced EMF means the spoke will behave as a battery, as a cell, whose EMF is this much volt. Okay. Now all the spokes are connected in parallel. See, all are connected in parallel. And if EMF developed across each spoke is same, then what is the net EMF? Net EMF is nothing but EMF of developed across one spokes. So across one spokes, it is 0.012 pi volts. So if it is 10, then also the net EMF will be 0.012 pi volts. If it is 20 in number, then also it will be same, because each spoke has same induced EMF, same induced EMF. And if so many cells are connected in parallel, then what is the net EMF? So net EMF is nothing but EMF of one cell. That is, if you have a parallel connection of n cell, each having same EMF, okay, so many. Then if each cell has EMF 2 volt, 2 volt, 2 volt, and all are connected in parallel. So what is net EMF? So this EMF is equal to the EMF of one cell. EMF of one cell. If you have two dry cell, 1.5 volt, 1.5 volt, connect them in parallel. So you will have the net EMF 2 volt on 1.5 volt only. But if you connect them in series, then net EMF will be 1.5 plus 1.5, E1 plus E2. Then it is 3 volt. And if they have different EMF, in that case, the net EMF will be given by E1 R2 plus E2 R1 divided by R1 plus R2. But it is not that case. In all the spokes, you have the same EMF, same EMF. So equivalent to cell connected in parallel of same EMF. So net EMF is equal to 0.012 pi volts and is independent of the number of spokes and is independent, right, somewhere independent of number of spokes connected between the axis and the ring. It doesn't matter whether you are connecting 100 spokes or 10 spokes or 1 spokes. The net induced EMF between the points, that is axial and the ring, is always this much volts. Am I clear to you? Yeah? Take the snapshot. Take the snapshot. Yeah. Take the snapshot. Done. And now, after doing a number of numerical problems, these are from NCERT books. You will find it is there in NCERT. Now, number may be changed. Some numerical value may be different in NCERT. But the way I am doing, you have to do this in the same way. Okay. Now, self-induction. Talking about self-induction. The new topic, self-induction. Okay. Now consider a coil. Coil. And resistance, you have studied about resistor. In electrostatics, you have studied about capacitor. Similarly, in magnetic effect of current or the EMI, electromagnetic induction, you have one circuit element called inductor. Like a resistor, capacitor, there is one element in magnetic effect, or you may say EMI, electromagnetic induction. This is called inductor. So inductor is nothing but a solenoid. It's nothing but a solenoid. So if an increasing current is flowing through this, I increasing, then you know what will happen? If an increasing current passes through the solenoid, then magnetic field inside the solenoid will also change, because magnetic field inside a solenoid, B is equal to mu naught Ni. Now N stands for number of turns per unit length, N for number of turns per unit length. per unit length. Unit length. Mu naught absolute permeability of free space or vacuum. If inside it is vacuum, then mu naught. And if you insert any ferromagnetic substance, then you have to take the relative permeability of the material. Mu r also. Then mu r will also come into picture. Okay. Now I, current flowing through the solenoid. Current flowing through the solenoid. Flowing through the solenoid. Now think what will happen. If I is increasing, obviously magnetic field will be increasing. And if magnetic field is increasing, then flux. Now assume that this circular turn. Then this circular turn has some area because of the radius pi r square is the area. So then magnetic field into area gives you the flux. So flux linked with the solenoid, linked with each turn is going to be changed. So if the flux linked with the solenoid changes, according to Lenz rule, whenever there is a change in, according to Faraday's rule, whenever there is a change in magnetic flux linked with a coil circuit occurs, an induced EMF is produced. And when the circuit is closed, induced current will be produced. Then that induced current, according to Lenz rule, has tendency to oppose the reason, the very cause which is producing it. The very reason is, since you are sending an increasing current through the solenoid, increasing current, so how will this coil will oppose it? So by developing, inducing a current along this direction. So this should be the direction of induced current. Induced current in the circuit. So induced current will be along this direction. So an induced current will flow in the circuit, and this induced current will always oppose the reason. Reason is increasing I. So how will you decrease this I? How will you decrease? So when the induced current is opposite to the flow of this current, then only it will be opposed. Now see the scenario. If you have the same solenoid and a decreasing I decreasing is flowing, then guess in what direction the induced current will flow? Induced current will flow in the circuit along same direction. Then only it will support the reason. Since the reason of production of induced current is the decrease in I, so this decrease will be supported by induced current flowing along the same direction. I am making it some another figure. Now if I is decreasing and is flowing from this direction, okay, then what should be the direction of induced current? I decreasing. So it should be along same direction. This is the direction of induced current. And this direction is given by Lenz rule. Induced current. But remember, the moment I becomes constant, then what will happen? Now flux will be there, but flux will remain constant. And if flux is constant, then E is equal to d phi by dt. If phi remains constant, then what about E? Induced EMF? 0. No induced EMF, no question of induced current. Then for constant current, no question of induced current or induced EMF in the circuit. So whenever an increasing or decreasing current is passed through a circuit, now I can make it some other diagram also. If you have a coil and you have a battery here and a switch. If you close the switch, okay, so now the switch is open, no current is flowing through the coil. If I ask you what is the flux linked with the coil, your answer will be 0. No current, no magnetic field, no question of magnetic flux, no question of change. Okay, now let us connect this switch. Now the switch is connected in the circuit. Switch is closed. What will happen? Now an increasing current starts flowing through the coil. An increasing current. Why? Earlier the current was zero when the switch was open. The moment you close the switch, now increasing current, I mean current starts growing from zero to some value. Zero to some value. So current starts growing. So growing current starts flowing through the circuit. Now think, the moment you open the switch, what will happen? Make and break. If you break the circuit, so current starts decaying. Decay of current will take place. Decay. Decay means start decreasing. So in both the condition, when current was increasing, then induced EMF, induced current will be set up in the circuit. So that induced current will flow in such a way, since I is increasing at the time of make of the circuit. So since the current is growing, so in what direction the induced current will develop? Along this direction. But at the time of break of the circuit, so when the current starts decreasing, this current is start decreasing, so then it will support the decrease. Means if the current I starts decreasing, then the induced current will be along the same direction. Then only it will be opposed by the decreasing. So since the induced current and this current are in same direction, that's why the decrease will be opposed. So this particular behavior, phenomena of the coil, property of the coil, by virtue of which it opposes both the growth and decay. Remember, the moment it attains its maximum value, the current becomes at its maximum value, the phenomena disappears. That is the phenomena by which it opposes the reason, I mean growing current should be opposed, decreasing current should be opposed. That phenomena of induced EMF will be abolished. The moment current becomes constant. Because once the current becomes constant, flux, magnetic field remains constant, flux remains constant, so no question of induced EMF, no question of induced current. Okay? Now, write down the definition of self-induction. Self-induction is the property. Now, I am writing here, self-induction is the property of a coil by virtue of which it opposes both the growth and decay. Growth and decay. You know the meaning of decay? Decreasing. It opposes both the growth and decay of current whenever a current passes through it. So this phenomena is called this property is called self-induction. So it is the property of a coil by virtue of which when a growing current or a decaying current is flowing in the circuit, then that growth or decay will be opposed. That particular property is called self-induction. Remember, this phenomena will disappear as soon as the current becomes maximum, attains its maximum value, becomes constant. This phenomena will disappear as soon as current I becomes constant. So if it starts growing, so 0, 0 0.1, 0.2, 0.5, 0. Ultimately the maximum value is 2 ampere. The battery can send a maximum current of 2 ampere. Then the current becomes steady. And the moment current becomes steady, there is a steady value. Now this induced EMF, induced current will disappear. This phenomena will disappear. So this phenomena exists only when the change continues. Only when the change continues. Change may be increasing, change may be decreasing. Increasing flux, decreasing flux. In both the cases, induced EMF is produced. Okay. Now this phenomena is called, one line you can write, it behaves, take the snapshot, I will write one more line. This is this is analogous to inertia and is called electrical inertia. Electrical inertia. What happens in inertia? If a body is at rest, it will remain to be at rest because of the inertia of rest property. If a body is in motion, it tries to be continue in motion because of inertia of motion property. So in the similar way, if so, this is analogous to self-induction self-induction is analogous to inertia in mechanics. In mechanics, it is also known as electrical inertia. Electrical inertia. So somehow, if the current wants to grow, its growing will be opposed. So at the time of break of the circuit, if the current wants to decay, it will oppose the decay. So that happens in inertia. If a body is at rest, now it opposes the force. Whatever you have applied the force, it will always oppose it. It does not want to go in motion. And if a body is in motion, it does not want to become in rest. So that's why it is analogous to the inertia in mechanics, known as electrical inertia. Now, self-inductance. Okay, should I wrap this part? So this part is, now I am talking about self-inductance, also known as coefficient of self-induction. Self-induction. Okay, you have a coil, current I through the coil is directly proportional to the flux linked with the coil. The more is the current, the more will be the magnetic field inside the solenoid, and then more will be the magnetic flux. Because flux linked with one coil, phi is equal to BA, and if you have total N coil, then it is NBA. And this B depends upon N, and B is mu naught Ni into A. So this phi flux is depending on I, current through the solenoid coil. So flux phi, if phi be the flux linked with the coil, when current I, remember phi is the total flux. I am not talking about the flux linked with one coil, one turn. A solenoid may consist of n turns. So if phi be the flux linked with a coil, when a current I flows through it, then phi is directly proportional to I. Means more current, more flux. Because current has relation with the magnetic field. If the current is increasing, I increasing means B increasing. If B increasing means flux, which is B into A, that also increasing. So flux increases. So flux is directly proportional to magnetic flux. is directly proportional to the current flowing through the coil. Now phi is equal to some constant L into I. Okay, this L is phi by I. L is called self inductance, self inductance, or coefficient of self induction. Coefficient of self induction. Self induction. Remember, self induction and coefficient of self induction are two different things. This L is called, L denoted by a symbol L, L is called phi by I. Now you can define, if you consider I is equal to 1 ampere, then L is equal to phi, means self inductance is numerically equal to the flux, because in unit the flux of phi is Weber, the flux of self inductance is Henry. I will tell you the unit of self inductance, so better I will write first unit of L. So phi is measured in Weber, Tesla meter square, also known as Weber. So WB, Weber divided by ampere, Weber per ampere. So Weber per ampere is nothing but called Henry. 1 Henry, Henry. In short, it is 1H, Henry. So Henry was the name of scientist, and in the honor of his name, it is then known as Henry, unit of self-inductance. So if I is equal to 1 ampere, then L is equal to phi. Now we are in a position to define phi. So phi is self-inductance of a coil is numerically equal to the flux, magnetic flux linked with it when unit current flows through the coil. So one can define it, mathematically you can define it. Have you taken the snapshot? I will write in the upper part. You just take it. Just take it. Okay, then L of a coil is numerically equal to flux. Flux means magnetic. I am not talking about electrical flux. Magnetic flux linked with the coil in which unit current is flowing. So then what is the magnetic flux? If you allow the 1 ampere current to pass through the solenoid or coil, any coil, this is also a coil. Okay, now allow current 1 ampere to pass through it. Now see the magnetic flux, total flux linked with the coil. Then that total flux is nothing but self-inductance of the coil. Self-inductance of the coil. Now you can define it some other way also. The other way to define it, okay, you know induced EMF E equals to minus d phi by dt. Remember phi for magnetic flux. So then mod of E is how much? D phi by dt. So this is d by dt of and phi. See, this phi is equal to Li. So this is L di by dt. If I write L, then this is mod of E divided by di by dt. Okay. Now this E, if we consider di by dt equal to 1 ampere per second, then L is equal to mod of E. Means self-inductance is again equal to the induced EMF developed in a coil when a varying current of rate of change unity flows through it. So if a current is flowing in the loop in such a way that its variation is 1 ampere per second, 1 ampere per second, then because of change in flux, an induced EMF will develop, and that induced EMF is numerically equal to the self-inductance, coefficient of self-induction. So let me write the another definition based on mathematical definition. I can say, so self-induction, again we are writing the definition. L of a coil, L means self-inductance of a coil is, again numerically, why numerically? Because they are different in units, numerically equal to EMF induced in a coil, when a varying current of rate of change unity, that is 1 ampere per second, flows through it. From here also the unit of L is Henry only, because unit of L, this is measured in volt, this is ampere per second, so this is volt second by ampere, this is also known as 1 Henry. So 1 Weber per ampere is also known as 1 Henry, and 1 volt second divided by 1 ampere, volt second per ampere, is also known as volt second per ampere, is also known as Henry. This is also known as Henry. So this way you have studied about the self-inductance of a coil, how will you define what is the unit of self-inductance, and then we will solve few conceptual problem, but today time is not allowing. I have already crossed the boundary. So